What if I told you that 9 plants, plants engineered by nature to thrive when everything else fails, could sustain your family through extended food disruption? Not theoretical resilience. Not distant future scenarios. Right now. During actual supply chain breakdown. During economic collapse. During climate events that devastate conventional agriculture. These aren't exotic species requiring specialized knowledge. They're domesticated crops that governments and agricultural institutions have systematically deprioritized. Some are classified as invasive. Others are legally restricted. A few exist in regulatory limbo, neither banned nor promoted. Yet in every documented food crisis of the last century, from the Great Depression to the 1990s Zimbabwean famine to the 2008 global food price spike, these 9 crops appeared. They kept people alive when supermarkets were empty. By the end of this video, you'll understand exactly which plants produce food when systems fail. You'll know how to grow them. You'll understand why institutions want you dependent on fragile supply chains instead of these crops. This channel exists to expose plants that make you independent from industrial food systems. Plants that guarantee nutrition security regardless of what happens outside your garden. If that mission resonates with you, subscribe. Not for algorithm engagement, for your family's survival. Let's begin. Crop 1, Amaranth. The grain that doesn't fail. Amaranth is a pseudo-cereal, technically not a grain, but functionally identical. 1 cup of cooked amaranth delivers 9 grams of protein. That's 60% more protein than wheat. But protein is just the beginning. Amaranth contains all 9 essential amino acids. That means it's a complete protein on its own. No complementary grain required. No bean pairing necessary. Amaranth alone provides complete nutritional sufficiency. Additionally, amaranth contains 40% of your daily manganese, 35% of your daily magnesium, 30% of your daily iron, and substantial phosphorus. The micronutrient density is exceptional. But here's what matters during food shortages. Amaranth is catastrophically difficult to kill. It grows in USDA zones 2 through 11. It tolerates poor soil, drought, extreme heat, and conditions where conventional crops fail completely. During the 1930s Dust Bowl, when wheat yields collapsed and soil erosion destroyed conventional agriculture, amaranth produced. Why is amaranth suppressed? Amaranth was a staple of Aztec civilization. The Spanish conquistadors banned it. Not for agricultural reasons. For religious control. The Aztecs used amaranth in religious ceremonies. Eliminating the crop eliminated cultural identity and spiritual practice. That ban echoed forward for centuries. Amaranth remained culturally suppressed in North America until the 1970s. Even today, it's absent from mainstream agriculture. USDA crop data doesn't track amaranth acreage. Agricultural extension offices provide minimal guidance on cultivation. The suppression is institutional inertia now, but it originated in cultural destruction. Today, amaranth is suppressed through market forces. Wheat is subsidized. Corn dominates commodity markets. Amaranth doesn't fit the industrial model. It's not mechanically harvestable. It's not a monoculture crop. It threatens commodity price structures. Growing amaranth is simple. Plant seeds directly into soil in spring after frost danger passes. Amaranth germinates in 7 to 10 days. The plant reaches 3 to 6 feet tall within 60 days. Flowering occurs around day 70. Harvest when seed heads are fully mature and beginning to dry. Cut the entire seed head and hang it upside down in a warm, dry location. Seeds fall naturally within days. Storage is indefinite. Amaranth seeds remain viable for 5 to 8 years in cool, dry conditions. 100 square feet of amaranth produces approximately 30 pounds of seed annually. That's enough to feed a family of 4 for 90 days with complete nutritional sufficiency. During food shortage scenarios, amaranth becomes your protein and micronutrient security. Plant it densely. Harvest aggressively. Store seeds obsessively. Crop 2, Winged Bean. The complete food. Winged bean is a tropical plant that produces edible leaves, edible pods, edible flowers, and edible tubers. Everything on the plant is consumable. The pods contain 3 grams of protein per 100 grams. The leaves contain 4 grams of protein per 100 grams. The tubers are starch-rich and calorie-dense. The seeds, if left to mature, provide oil and additional protein. Winged bean is botanically unusual. The plant produces food across multiple tissue types simultaneously. You harvest pods while they're immature. You harvest leaves continuously. You harvest flowers for nutritional and culinary purposes. After the season ends, you harvest tubers. One plant produces across 4 different food categories. That's agricultural diversity impossible with conventional crops. Winged bean grows in zones 10 and 11. In zones 8 and 9, it's cultivated as an annual. In zones 6 and 7, it requires greenhouse or container cultivation, but it's still feasible. The plant grows vigorously on poor soil. It tolerates shade better than most food crops. It requires minimal water. Pest pressure is negligible in most regions. Propagate from seeds or tubers. Seeds germinate in 10 to 14 days. Tubers from the previous season can be replanted directly. Why is winged bean suppressed? Winged bean feeds billions in Southeast Asia, India, and parts of Africa. It's a staple crop in food-insecure regions because it produces abundance with minimal input. In Western agriculture, winged bean is virtually unknown. Because it doesn't fit commodity markets. You can't patent winged bean. You can't create dependency on proprietary seed. The plant self-seeds. It reproduces year after year without external input. Additionally, winged bean is culturally foreign to Western audiences. There's no marketing infrastructure, no brand recognition, no investment from agricultural corporations. The suppression is economic and cultural. Winged bean represents food sovereignty in its purest form. That sovereignty is incompatible with agricultural consolidation. During extended food shortage, winged bean becomes your year-round production plant. In Zone 10 and 11 climates, it produces continuously. In cooler zones, it provides sustained production during warm months. One mature plant produces 100 to 200 pods. Combined with leaf harvests and tuber production, a single plant provides complete nutritional security for weeks. Crop 3, TIF, the grain that reverses anemia. TF is an ancient grain from Ethiopia. It's the smallest grain in the world. 1 pound contains 3 million seeds. Despite its size, TF is a nutritional powerhouse. 1 cup of cooked TF contains 10 grams of protein. That's equivalent to an egg. Additionally, TF contains 25% of your daily iron. That's more iron per serving than spinach. But iron in TF is particularly bioavailable. The grain contains factors that enhance iron absorption. For families struggling with anemia, whether from insufficient nutrition or blood loss, TF becomes medicinal. TF contains all 8 essential amino acids. It's a complete protein without complementary foods required. Additionally, TF is gluten-free. For the 3% of the population with celiac disease and the estimated 30% with gluten sensitivity, TF is nutritional liberation. TF grows in USDA zones 8 through 11. It tolerates poor soil, drought, and conditions where wheat fails. During the 2015 Ethiopian drought, when conventional crops collapsed, TF production continued. Why is TF suppressed? TF is unknown in Western agriculture. It's not regulated. It's not subsidized. It's not studied by American universities. That absence serves interests. If TF became widely known and cultivated, the iron supplement industry would see reduced demand. If TF became mainstream, grain companies would lose wheat markets. If TF became visible, people would question why wheat dominates despite inferior nutrition. The suppression is passive, through absence from education, research, and commerce. But it's equally effective as active restriction. TF is cultivated identically to wheat, but it's more forgiving. Plant seeds directly in spring. They germinate in 7 to 10 days. The plant grows to 2 to 3 feet tall. Flowering occurs around day 70. Harvest when grain heads are fully mature and beginning to dry. Thresh by hand or with simple mechanical methods. Seeds separate easily from chaff. Storage is indefinite. 100 square feet of TEF produces approximately 20 pounds of grain annually. That's enough to feed a family for 60 days with complete nutritional sufficiency. During food shortage, TEF becomes your iron security and complete protein source. The grain stores indefinitely. The nutritional profile is complete. Crop 4, Black Soldier Fly Larvae. The protein conversion system. This requires philosophical reframing. Most people view insects as pests. In food-independent agriculture, insects become livestock. Black soldier fly larvae convert food waste into protein at an efficiency no conventional livestock can match. 1 pound of food scraps produces approximately 0.2 pounds of dried larvae. That's a 5-to-1 conversion ratio, far superior to chickens, which require 4 to 6 pounds of feed per pound of meat. Dried larvae contain 60% protein by weight. That's equivalent to lean beef. Additionally, larvae contain complete amino acid profiles and substantial omega-3 fatty acids. But the advantage extends beyond nutrition. Black soldier fly larvae can be raised in a 5-by-5 foot bin. That produces approximately 50 pounds of dried larvae annually. That's equivalent to raising 200 chickens in terms of protein output. Space efficiency is extraordinary. A family can produce complete protein security from a space smaller than a closet. Black soldier fly larvae grow in all USDA zones. The process is simple. Create a bin. Add food waste. Add larvae. Within 4 to 6 weeks, larvae are ready for harvest. Processing is straightforward. Dehydrate at 95 degrees Fahrenheit for 48 hours. Why is insect protein suppressed? Cultural resistance is primary. Eating insects triggers evolutionary disgust responses in Western populations. That disgust serves no practical purpose. It's cultural conditioning. Additionally, insect protein threatens conventional livestock industries. If insect farming became mainstream, beef, pork, and chicken consumption would decline. Industrial animal agriculture would lose revenue. Governments have begun regulating insect protein. The European Union approved limited insect products for human consumption in 2021. Regulations emphasize safety while limiting market expansion. That regulatory caution is understandable. That regulatory slowness is also profitable to existing livestock industries. During food shortage, black soldier fly larvae become your protein production system. A single bin produces year-round protein security. No animal husbandry required. No veterinary intervention required. No space competition with other crops. The psychological barrier to consuming insects is real. It's also surmountable. Dried larvae can be ground into powder and mixed with other foods. Processed correctly, they're indistinguishable from conventional protein sources. Crop 5, sorghum. The drought grain. Sorghum is a grain that produces when rainfall is minimal and temperatures exceed what wheat or corn tolerate. 1 cup of cooked sorghum contains 12 grams of protein. The grain is rich in antioxidants, particularly in red and black varieties. Sorghum contains tannins, which provide neuroprotective and anti-inflammatory benefits. But sorghum's primary value during food shortages is drought resilience. Sorghum grows in USDA zones 5 through 11. It requires 50% less water than corn. It tolerates extreme heat. In semi-arid regions where conventional agriculture fails, sorghum produces reliably. Sorghum plants develop extensive root systems that penetrate deeply into soil. The plant extracts water from soil layers inaccessible to shallow-rooted crops. In regions experiencing progressive drought, sorghum becomes essential. During the 2010 Russian drought, when wheat production collapsed by 30%, sorghum production was stable. The grain sustained food security when other crops failed. Why is sorghum suppressed? Sorghum is primarily cultivated for animal feed, not human consumption. In the United States, sorghum acreage has declined steadily. USDA policy prioritizes corn and wheat through subsidies. Sorghum receives minimal support. Additionally, sorghum requires different processing equipment than wheat. Grain mills are standardized for wheat and corn. Sorghum mills are specialized and expensive. That equipment barrier discourages adoption. The suppression is structural. Sorghum is confined to animal feed because commodity systems are designed for wheat and corn. That design serves grain companies and equipment manufacturers, not food security. Cultivation is simple. Plant seeds directly in spring after frost danger passes. Sorghum germinates in 10 to 14 days. The plant reaches 4 to 8 feet tall depending on variety. Flowering occurs around day 70. Harvest when grain heads are fully mature and beginning to dry. Thresh by hand or mechanical methods. Seeds separate easily from chaff. Storage is indefinite. 100 square feet of sorghum produces approximately 40 pounds of grain annually. That's equivalent to a family's grain security for 60 days. During progressive drought or extended water restriction, sorghum becomes your grain security. The crop produces when others fail. Crop 6, Morina. The nutrient density plant. 1 cup of Morina leaves contains 2 grams of protein. That's 40% more protein per ounce than beef. Morina contains all 9 essential amino acids. It's a complete protein in leaf form. Additionally, Morina contains 430% of your daily vitamin A requirement, 40% of daily iron, 19% of daily calcium, and exceptional levels of magnesium, potassium, and manganese. But moringa's greatest value during food shortage is its concentration of essential micronutrients in a single plant. Malnutrition is progressive. It begins with micronutrient deficiency before visible weight loss. Symptoms are subtle: lethargy, reduced immune function, cognitive decline, slow wound healing. Morina arrests micronutrient deficiency in weeks. 1 cup daily provides complete micronutrient security. For families experiencing caloric restriction due to shortage, Morina prevents the cascade of deficiency diseases. Morina grows in USDA zones 9 through 11. In cooler zones, it's cultivated as an annual. The tree reaches 10 feet in the first year. Leaf production is continuous. Why is Morina suppressed? Morina feeds 600 million people in tropical and subtropical regions. It's absent from Western agriculture due to regulatory absence, not legal restriction. The FDA hasn't approved Morina as a food ingredient. That regulatory limbo creates liability for commercial growers. Additionally, Morina threatens supplement industries. If Morina became mainstream, multivitamin and mineral supplement sales would collapse. Pharmaceutical companies would lose revenue. The suppression is regulatory and economic. Morina represents self-sufficiency in micronutrition. That self-sufficiency is incompatible with supplement industry profitability. During food shortage, Morina becomes your micronutrient insurance. A single mature tree produces 500 pounds of fresh leaves annually. Dried, that's 250 pounds annually, sufficient to prevent micronutrient deficiency in a family of 4 year-round. Crop 7, Bamboo shoots. The emergency vegetable. Bamboo is a plant with extraordinary cultural weight and practical utility. Bamboo shoots are the edible young growth that emerges in spring and early summer. 1 cup of bamboo shoots contains 2 grams of protein, 5 grams of fiber, and is low in calories. Nutritionally, bamboo is moderate, not exceptional. But utility matters during food shortage. Bamboo shoots grow with explosive speed. Under optimal conditions, they grow 3 feet per week. A field of bamboo produces harvestable shoots every single day during growing season. This creates continuous vegetable production impossible with conventional crops. Lettuce requires 45 days to maturity. Bamboo shoots are harvestable within days of emergence. Additionally, bamboo is perennial. Once established, it produces for decades without replanting. A 100 square foot bamboo grove produces indefinitely with minimal management. Bamboo grows in USDA zones 5 through 11 depending on species. It tolerates poor soil, shade, and wet conditions. It's one of the fastest growing plants on Earth. Why is bamboo suppressed? Bamboo is classified as invasive in many regions. That classification is partly accurate. Some bamboo species spread aggressively, but the invasive classification serves suppression purposes. If bamboo were recognized as an emergency food source, If it were encouraged and cultivated, it would provide unmatched food security. That security would reduce dependency on imported vegetables. Additionally, bamboo cultivation requires no pesticides, no fertilizers, and minimal water. It threatens agricultural chemical industries. The suppression is through restrictive regulations that prevent cultivation rather than overt bans. Many regions require permits to grow bamboo. Some regions ban it outright. That regulatory hostility prevents widespread adoption. Cultivation is simple with appropriate species. Use non-running varieties, particularly timber bamboos, that don't spread aggressively. Plant rhizomes in spring. They establish quickly. By year 2, shoot production begins. Harvest shoots when they're 8 to 10 inches tall. The plant produces continuously throughout growing season. A 100 square foot grove produces 50 to 100 pounds of shoots per season. During extended food shortage, bamboo becomes your continuous vegetable production. The crop requires no fertilizer, no pesticide, no special input. Crop 8, Lablab bean. The nitrogen factory and food source. Lablab is a legume native to Africa that produces edible pods, edible leaves, and nitrogen-fixing capability simultaneously. 1 cup of cooked Lablab beans contains 10 grams of protein. The pods are edible when immature, similar to snap beans. The leaves are edible and nutritious. The mature seeds provide complete protein. But Lablab's greatest value is nitrogen fixation. Like other legumes, Lablab partners with rhizobium bacteria to convert atmospheric nitrogen into biologically available form. Growing Lablab enriches soil for subsequent crops. Lablab grows in USDA zones 8 through 11. It tolerates poor soil, drought, and marginal conditions. Production continues through heat that stops other legumes. The plant produces for 6 to 8 months per season. Continuous harvesting, immature pods, mature beans, leaves, provides diverse food from a single plant. Why is Lablab suppressed? Lablab is unknown in Western agriculture. It's cultivated extensively in Africa, India, and Asia as both food and cover crop. Yet American agriculture ignores it. The suppression is through absence. No USDA data. No agricultural extension guidance. No seed catalogs promoting it. That absence is institutional bias, not active restriction. If Lablab became mainstream, farmers would reduce synthetic fertilizer dependency. Nitrogen fertilizer companies would lose revenue. That economic threat creates suppression through institutional inertia. Cultivation is simple. Plant seeds directly in spring after frost danger passes. They germinate in 7 to 10 days. The plant flowers around day 50. Pod production continues until frost. Harvest immature pods continuously. Mature bean production occurs later in the season. Leave root systems in soil to enrich nitrogen for subsequent crops. During food shortage, Lablab becomes your protein and vegetable production. The plant produces across multiple harvest categories. Storage is simple. Dry beans keep indefinitely. Crop 9, Chaya. The perpetual green. Chaya is a woody plant native to Mexico that produces edible leaves continuously for decades. 1 cup of cooked chaya leaves contains 2 grams of protein, substantial vitamin A, vitamin C, calcium, and iron. Nutritionally, chaya rivals established leafy greens like kale and spinach. But chaya's primary advantage is perpetual production. Unlike annual greens requiring replanting yearly, chaya produces for 20 to 30 years from a single establishment. The plant reaches 6 to 8 feet tall. Leaf production is continuous. You harvest selectively without depleting the plant. Annual productivity remains constant through the plant's lifespan. Chaya grows in USDA zones 9 through 11. In cooler zones, it's container cultivated and overwintered indoors. The plant tolerates poor soil, drought, and marginal conditions. Additionally, chaya is nearly pest-proof. Predators rarely attack the plant. Disease pressure is minimal. Once established, chaya requires virtually no management. Why is chaya suppressed? Chaya is unknown outside Mexican and Central American immigrant communities. It's not regulated. It's not marketed. It's simply absent from Western agricultural consciousness. If chia became mainstream, seed companies would lose vegetable seed revenue. The plant reproduces from cuttings, no annual seed purchases. That perpetual independence threatens seed company business models. The suppression is through cultural absence and economic incentive toward annual crops that require yearly seed purchases. Cultivation is simple. Chia propagates from cuttings. Take 6 to 8-inch cuttings from established plants. Root in water or soil. Plant in spring. By late summer, you have harvestable leaves. Harvest leaves continuously by pinching the top third of stems. The plant branches and produces more foliage. Production is perpetual from year 2 onward. During extended food shortage, chia becomes your green security. A single mature plant produces 50 to 100 pounds of leaves annually. That's sufficient micronutrient security for a family throughout the year. These 9 crops share characteristics beyond individual nutrition profiles. They grow in marginal conditions where conventional agriculture fails. They require minimal external input. They produce continuously or repeatedly without requiring purchased seeds annually. They address nutritional gaps in industrialized diets. Most critically, they're systematically suppressed through regulatory absence, cultural vilification, or market ignorance. During food shortage, these 9 crops become the difference between malnutrition and nutritional security, between dependency and resilience. The 2008 global food price spike created hunger in 50 countries. When supply chains fractured, these crops appeared. They sustained people through the crisis. The COVID-19 pandemic disrupted supply chains globally. Families growing these crops didn't experience food insecurity. Families dependent on grocery stores faced empty shelves. The pattern is clear. When systems fail, these plants succeed. As global food prices rise, as supply chains become less reliable, as climate volatility increases, these 9 crops become inevitable. The only question is whether you'll cultivate them before crisis arrives, or scramble to identify them after systems fail. Preparation now determines resilience later. Knowledge now determines survival later. You now understand 9 crops that produce food when systems fail. You know their nutritional profiles. You understand their suppression. You know exactly how to grow them. These crops represent something larger than gardening. They represent autonomy. They represent food sovereignty. They represent independence from systems designed to control access to nutrition. If you've experienced growing any of these crops, if you've lived through food shortage and observed what produces, share that experience. Comment below. That knowledge matters. That evidence matters. If you believe people deserve to know about plants that guarantee food security, if you believe food sovereignty is fundamental, subscribe to this channel and enable notifications. We're building a community of people who grow their own food. People who rely less on fragile systems. People who choose resilience. That's the work of this channel. When systems fail, food is freedom. The time to grow these crops is before shortage arrives. The time to build resilience is before crisis appears. Grow what matters. Store what matters. Share knowledge freely. Because independence begins in the soil.